Good evening, everyone. I'm Shivani Dhok and I welcome you all for the week 5 tutorial for the course of Simulations of Communication Systems using MATLAB. So, like every week, this week's tutorial will be divided into two parts. First one will be recap of week 5 content, followed by the questions related to them. So, quickly, let's start with the recap of week 5 content. So, this week 5 was entirely related to random processes. So this random process, we can define it in multiple ways. One way is to consider it as a sequence of random variables. That is, sequence of, let's say, time variables with respect to time. Sorry. Or if you have a time index at each time t, so you will have multiple sample functions like this. And if you sample at each time t, then you can get multiple possible, let's say, xt of omega 1, xt of omega 2, and so on. So in this way, you can consider it as a sequence of random variables. And another way to look at it is you have a sample space omega, and then you can have a small little omega, which is outcome of one event, and then you have some multidimensional space, let's say, and which will have some, let me just draw something like this. You will have some multi-dimensional space where each dimension will correspond to one time index, and then this omega will map to xt1 of omega, xt2 of omega, and so on. Or you can write it as x of t comma omega. So here this omega, one omega will give multiple values for different multiple values at each time index. So this will be like x of something comma omega. So this is a random process. Then this random process can be completely characterized by what is known as finite dimension distribution or nth order CDF or nth order PDF. So nth order CDF PDF, by that we mean it will be joint. So what do we mean by nth order joint PDF? So nth order joint CDF, we can write it as f x1, x2, and so on till xn, x1, little x2, and so on till little xn. And this is nothing but probability that your x1 is less than or equal to little x1, x2 is less than or equal to little x2, and so on till xn is less than or equal to little xn. And similarly, you can have our nth order joint PDF, and this you can get by having a nth order derivative with respect to your all the n variables of x1, x2, and so on xn, that is your nth order CDF. After that, we looked at different properties or different statistics of a random process. So let's say x of t is a random process that we will be looking at. So this mean mu t is simply expectation of xt. Then you have autocorrelation. So this Rx of T1, T2, this you can write as expectation of x of T1, x of T2 conjugate, or if you are writing it in terms of time and delay, then you can write it as expectation of x of t into x conjugate of t plus tau. Then you have another concept that is known as autocovariance. So this autocovariance is simply expectation of x of t minus mu of t into x of t plus tau minus mu of t plus tau conjugate, and this we can write as cx of t tau. Same way. And similarly we have another concept. So if we have two random processes, so let xt and yt be two random processes, then the cross correlation of xt and yt is given as rxy of t tau. Let's take the delay definition. So this will be simply expectation of x of t into y conjugate of t plus tau. So this is called two random processes. So that's why it is called cross. If it is correlation with itself, then we'll say it as autocorrelation. Okay. After that, we looked at some properties or some different classes of uh, random processes, and so here first thing that we looked at is strict sense stationary, which we can also write as SSS process. So here what happens is your PDF or CDF, it will follow. So if I consider nth order PDF CDF, then if I have x of t1, x of t2 and so on till x of tn, x1, x2 and so on till xn, this will be exactly equal to, if I delay each and every one by sum. So x of t1 plus tau, x of t2 plus tau, so on till x of tn plus tau, but evaluated at same point. That is, your distribution is invariant to your delay. So if you delay it by same time duration, then its PDF CDF remains same. So this is strict sense stationary. This is stricter version. We have a little diluted version, and that is known as wide sense stationary. So this is WSS. So here what happens is, first thing, your mean is a constant, and second thing, your autocovariance or autocorrelation, let's say, is only a function of lag. If these two things happen, then Then the random process is known as a wide sense stationary process. We'll take some examples for this. After that, we looked at another class which is known as ergodic processes. So in this ergodic process, what we say is if this time average and ensemble average, if they are equal, then the process is known as ergodic process. Till it is mentioned explicitly in our wireless communication course, we'll just consider ergodic processes. After that, we looked at Gaussian random process. So in Gaussian random process, your xt1, xt2, and so on all follow some Gaussian distribution. And then in Gaussian random process, an interesting property is wide sense stationary implies strict sense stationary. So this is an interesting property for Gaussian random process. After that, we have looked at what is known as vectorization. So we can write these random processes in the form of a random vector. Right? We can write it as, let's say, xn as a vector, that is x1, x2, and so on till xn. Then its mean mu n can be simply written as another vector, that is expectation of x1 and so on till expectation of xn. And we can write its autocovariant, or let's say autocorrelation matrix. Let's write it like this: Rn as expectation of xn, xn Hermitian. So that will give the autocorrelation or autocovariance matrix. Then we looked at how, so if we have xn and now if we get xn plus 1, which we can write as xn, that is vector which we had, and xn plus 1. So this is an additional entry. This is a vector. So when you have this underline coming up, it will be a vector. Otherwise, it will be a scalar quantity. That will be a general rule that we'll be using throughout the course. Then we can write this x of mu n plus 1 vector as mu n vector, and just append it by expectation of n plus 1. Similarly, if I want to find Rn plus 1, that is a matrix, that is simply expectation of this vector xn plus 1 Hermitian. With this we can write as expectation of xn plus 1 into xn Hermitian into xn plus 1 conjugate. Then what we will be having is simply expectation of xn Hermitian, xn into xn plus 1 conjugate into xn plus 1 into xn Hermitian into xn plus 1 into xn plus 1 conjugate. So this first element that we are having is simply Rn. This thing that we are having is Rxn plus 1, and then you have some additional vectors and scale vectors coming up here. So this is how you can do it. So if you know what is Rn and you know what your Xn was, so you can just take your Rn and add these three quantities, new quantities, to create your Rn plus 1. After that, we looked at another thing that is known as power spectral density. The key point that we'll take from that is your autocorrelation function. and your power spectral density. So these are Fourier transform pairs. After that, we looked at what is known as a White process. So this White process, what it means is your power spectral density, it is flat, which means that it is not a function of frequency, or rather it is a constant function of frequency. And that if that is the case, then your autocorrelation function will be an impulse. And then we looked at another important thing for communication systems, and that is known as your AWGN. So here your A stands for additive, which means that it gets added to your signal. Then it is white. So what does white mean? Its PSD is flat. Then you have Gaussian. So it is a Gaussian process, that is sample every sample follows Gaussian distribution, and it is noise. So this N basically stands for noise. So your noise is a random process which gets added to your signal and has white PSD, or has a flat PSD, that is, it is a white process, and every sample or whatever sample you take from that random process follows a Gaussian distribution. And this is your additive white Gaussian noise, which we will be looking at throughout your wireless communication course. So what we generally take is, if your N of T is AWGN, then we generally take that your RNN of tau is taken as N0 by 2 delta tau, which means the power spectral density will be N0 by 2. And another thing that we take is this expectation of N of T as 0. So these are few things that we consider in general when we are looking at additive white Gaussian noise. Okay, just for completeness, we write here. Okay, so that's all for this week's content. If you have any questions, then feel free to ask. Otherwise, I'll quickly move on to the questions part. Okay, so let me move on to the first question. So here the first 5 questions are from last year's assignment, and remaining 5 are from some other assignments. So let's start. So the first question here says that, which of the following statements are true? Your option 1 is all the entries of a random sequence are identically distributed. Second option is a random sequence becomes deterministic if the experimental outcome generating it is known. Then the third option is the entries of a random sequence are necessarily independent of each other. D, all of the above. So the uh, first first option says that, so this option here says that if you have x1, x2 and so on till x3, x4 and so on, and it says that all of these x1, x2, x3 and x4 are identically distributed. So for a random process, all of these samples of time that we are having, that is at time equal to 1, time equal to 2 and so on, at each time we might get a different distribution. These are not identically distributed, so first option is not correct. Let's look at the third option. The entries of a random sequence are necessarily independent of each other. Again, these x1, x2, x3, x4 and so on may be correlated or dependent, which means that these are not independent. So your third option is also wrong, which means that anyway all of the above is gone. Then what is remaining is your second option. It says that a random sequence becomes deterministic if the experimental outcome generating it is known. So that takes us to that definition, that is that gives us mapping. So you have your sample space. You have a sample space. Let's call it omega. And in general, what happens is random variables or random processes or random vectors are mapping. So let's say I have an n-dimensional, let me just draw some abstract space. Let it be like this one. So let's say I have this T1, T2 and T3 and I'm just looking at example. For example, third order mapping I'm looking at, and the sample space will have some little omega, and then what we will have is we'll be having it as a mapping from here, that is from your sample space to some point here, that will be x of xt1 of omega, xt2 of omega and so on. So this will be your mapping xt1 of omega, xt2 of omega and so on. Okay, and this xt1, xt2, so this xti is a function, and this function is deterministic. There is no randomness in this function. The randomness is based on only the selection of this omega. So whatever randomness comes up is only here. So the randomness, entire randomness, comes from the choice of, or the random choice of omega, and this omega is from your sample space, that is capital Omega. Okay, so now if someone says that I tell you what your little omega is, that is, I tell you what your outcome is, and we know that these xti's are a deterministic function, it clearly means that if I know what is omega, if I deterministically know what my function x of ti is, I can easily understand what the value of this xt1 of omega, xt2 of omega, and so on is. So that is exactly what your second option is saying. It says that a random sequence becomes deterministic if the experimental outcome generating it is known. So if we know the experimental outcome generating that, that is, if I know this omega, then the value of the random sequence is deterministic completely. We know what exactly we are going to get here, which means that the option 2 is correct. I suppose any questions in this first part? If not, there I see some comment, I'll look into it. If you have any question in this part, then let me know. Okay, so someone is asking in chat box that there is some error in grading of answers for assignments in week 1, 2, 3. The answer keys provided is not the answers used for grading the assignments. Is there something that could be done from my end? I don't handle these assignment stuff, and generally NPTEL people and the course coordinator handles it. I have seen the portal where you ask, or I've seen your Q&A for portal, and I see that many of you have posted queries about it, and I think they haven't replied to it. Last year or in last semester also, there was some course in which I was TA. There were some issues in grading of those assignments, but at the end NPTEL people and the course coordinator had handled it. However, still I'll try dropping a mail to NPTEL people and asking them if anything can be done quickly, or at least can there be some response from the course coordinator or the NPTEL team. Another thing, if you are able to find some help or in general query portal for NPTEL, then you can just put a mail there. In general, I can't do anything. I can drop a mail to these people from my end, that I'll do. But last semester, it was done by the end of, like, by the end of your final result or final exam, these people had done or re-evaluated everything when students had asked for these things. It was done last year. Okay. If there are no further questions, I'll quickly move on to the next question. Okay. So the next question says a random process is called stationary in the wide sense when. The first option is the CDF is independent of time regardless of the order. Second option is the mean function is independent of time. Third option is the correlation function is independent of time, and fourth option is both the mean function and the autocorrelation functions are independent of time. So if you observe here, this is not something what is known as wide. This is not a definition for wide sense stationary. Then we have the mean function is independent of time. In this option, nothing is said about correlation. So again, this is not correct. This is not correct. Third option, the correlation function is independent of time. In this particular case, nothing is said. about mean. So this is also not a correct statement. The last statement is both the mean function and the autocorrelation functions are independent of time. So your mean function is anyway expectation of your xt, and if it is some constant c for all t, and if it is not a function of t, it is some constant c for all t. And then you have your autocorrelation function, that is x of t into x conjugate of t plus tau. This is only a function of your delay, that is rx of tau. This is basically the definition what this thing is saying, and this is your definition of the Whiteson stationary process. Therefore, the correct option is 4. This is simple definition chasing. It's not that difficult till this point. Any questions? Okay, if there are no questions, then let me quickly move on to the next question. So the next question here says that the Gaussian process can be completely characterized by its mean and autocovariance function. So is this thing true or false? So if you look at, so for understanding this, what we will do is we will consider nth order joint PDF or nth order joint PDF of random process xt, which I'll write, or which is equivalent to writing xt like this. Okay, so that is simply x of t1, x of t2, and so on till x of tn into x1, x2, and so on till xn. And this we can write as 1 upon 2 pi to the power n by 2 into determinant of covariance matrix, let's say Cn, to the power 1 by 2 or square root of that. Then we will have exponential function of half into x minus mu n transpose Cn inverse. Let me bring it down here, into x minus mu n. So here your vector x is simply x1, x2, and so on till xn transpose. Your vector mu n is simply mu of t1, that is mean of all of these things. And then your covariance matrix Cn here is expectation of, or rather you can write it as Rn minus mu n transpose, where your Rn is simply expectation of xn transpose, it's real, where your xn is again collection of x of t1 and so on till x of tn transpose. So again, if you observe carefully, that this is the PDF, and PDF of a continuous random variable or continuous random process completely defines its distribution. So this entire PDF is only a function of your covariance matrix and mean. So your PDF is only a function of, or only depends on, Cn and your mean vector mu n, which is which is nothing but your autocovariance function and its mean. Which means that if I know our mean and autocovariance function, we completely characterize the Gaussian process, and therefore this is a correct statement. So the statement is. Any questions here? Okay, if there are no questions, I'll move on to the next question. So the next question says that the power spectral density of a random process is option 1, the Fourier transform of its autocorrelation function. Second, the square of its Fourier transform. Third, the square of the absolute value of its Fourier transform. Fourth, both 1 and 2. So we have seen this already, and it is one of the key property for your random process. So we have seen that power spectral density of a random process. So PST, and let me write it like this: autocorrelation function and your power spectral density. These are Fourier transform pairs. We have seen this already. If there are any questions, then you can ask. Otherwise, I'll move on to the next question. Okay. So the fifth question says that a random process x of t is called white when 1. Its PSD is flat. Yeah, this we know by definition. This option is correct. Its PSD is flat. Second option says that the correlation function is flat in lag. So if your autocovariance function is like this, some constant, then in frequency domain, when you take its PSD, then that will be some delta f, c into delta f, something like this. So this will be impulsion frequency, which means it is not flat. Then you have autocorrelation function is flat in lag. These two options are already same. It makes no sense. So these both are wrong. And then it says that PSD is an impulse function. So if autocorrelation, again, this is same. If autocorrelation function is flat in lag, then your PSD is an impulse function that we just saw. It is because of your Fourier transform impulse and constant function Fourier transform duality. So by definition, we have that the random process xt is white when the power spectral density is flat in power spectral density is flat. So by definition, a random process xt is white if the power spectral density or PSD is flat, that is constant with respect to frequency. Okay, any question here? Okay, if not, I'll move on to the next question. So from now, these are some other questions which are not a part of, not which were not a part of last year's assignment. These are some additional questions which will help you understand some properties of your white sense stationary processes and some properties of your AWGN process. One question I have taken on purpose, which will be helpful in your coming assignments or coming weeks content. So let's start with question 6. So it says that consider a random process xt. So what is given to us is this random process xt, and this is the definition of your random process. And here this thing here, sorry, yeah, this t is simply indicating the time, and this u here is the source of randomness. Okay, and this u it is given to us is distributed like this. This is so this u is uniform distributed. So this symbol here, this implies u is a uniform random variable in the interval 0 to 2 pi. Okay, so we had seen what is uniform random variable in the first lecture. Still, I'll just write down its PDF. So this fu of little u, which is PDF, is equal to 1 over 2 pi if the little u belongs to the interval 0 to 2 pi, and it is 0 otherwise. Okay, now what is asked to us is xt a wide sense stationary process? So we need to figure out whether the given random process is wide sense stationary or not. So how to do that? We have two checks for checking whether it is a wide sense stationary. So step 1 is check if mean is constant, and then if your step 1 is correct or it is all right, then we need to check if autocorrelation function or your autocorrelation is only a function of lag. Okay, so let's start with step 1. So we have step 1, and for that we'll find out what is x of t. So that means we need to find out expectation of what is your xt. Xt is simply cos t plus u. And the source of randomness is u. So this is your source of randomness. And this is like some function of random variable u. So it's like finding expectation of the function of a random variable, and this thing is simply integral fu of u into the function cos of t plus u du. So this is standard property of expectation of functions of a random variable. If you want to know how this happens, you can refer to some random variable textbook. I won't go into its details. So therefore we have this expectation of x of t as, what is here fu of u? It is 1 over 2 pi, only in range of 0 to 2 pi, otherwise it is 0. So we can write it as integral 0 to 2 pi, because otherwise here PDF, this quantity here, will be equal to 0. And in this range it is a constant into cos of t plus u du. Then 1 over 2 pi here, integration of cos is sine t plus u from 0 to 2 pi. This will give me 1 over 2 pi sine of 2 pi plus t minus sine of t. So this is 1 over 2 pi. Sine of 2 pi plus t is again sine t minus sine t. This is equal to 0. So basically you are integrating a cosine function over its period. So that will anyway give us 0. So your expectation of t is, expectation of xt is 0, which is a constant. This means that step 1 is checked. Let me number this as equation 1. Now if your mean is constant with respect to time, now let us move on to the step 2. That is, let us find out expectation of x of t into x of t plus tau. It is a real random process, so it's okay. So this is simply, we can write it as expectation of your xt is cos of t plus u, and then your x of t plus tau will be cos of t plus u plus tau. Again, the source of randomness is same random variable, that is u. So you can write this as integral from 0 to 2 pi. It's PDF 1 over 2 pi. So this quantity here is fu of u multiplied by the function, that is cos of t plus u into cos of t plus u plus tau du. And now here we can apply cos A cos B formula. So this is equal to 1 over 2 pi, I can take it outside, into 0 to 2 pi. Then we have cos cos A cos B, so that is simply 1/2 into cos of A plus B, that is 2t plus 2u plus tau, plus cos of A minus B, so that will be simply cos of tau du. So let me separate it into two integrals. So this is equal to, so what we have is expectation of xt into x of t plus tau. This is equal to 1 upon 4 pi integral 0 to 2 pi cos of 2t plus 2u plus tau du, plus 1 upon 4 pi into, again this cos tau is independent of u, I can take it outside, cos of tau integral 0 to 2 pi du. So the second integral, this is simply equal to 1 upon 4 pi into cos of tau into 2 pi. So this is equal to 1 by 2 cos tau. Okay, and now we need to evaluate what the first integral is. So this is equal to 1 by 2, or let me write it like this, cos of tau by 2 plus 1 upon 4 pi into cos of 2t plus 2u plus tau upon 2 from 0 to 2 pi. So this thing is equal to cos of tau by 2 plus 1 upon 8 pi. We have cos of 4 pi plus 2t plus tau minus cos of 2t plus tau. Again this thing here, cos of 4 pi plus 2t, this thing is equal to cos of 2t plus tau, which means that this gets cancelled and reduces to 0. So what we have here is simply cos of tau plus 2. So what we obtain is the autocorrelation function, which is expectation of x of t plus x into expectation of x of t plus tau, comes out to be equal to half of cos of tau. And again, if you observe, this is only a function of lag, and this is again independent of time and only a function of lag. And so this implies that your step 2 is also checked. Okay, so now what you have is your step 1 is true, your step 2 is also true, and therefore from, let me number it as equation 2. So what we can conclude is from 1 and 2, it clearly implies that, or let me write it properly. You can write that since expectation of x of t is 0, that is constant, and expectation of x of t into x of t plus tau is half cos tau, which is function of lag only. Therefore x of t is wide sense stationary. Is this clear? Any questions? Okay, if there are no questions, then let me move on to the next question. So the next question says, let xt and yt for t in real be jointly wide sense stationary processes. Consider zt equal to xt plus yt, and we need to show that zt is a wide sense stationary process. So there is something called as jointly wide sense stationary. So let me first define that. So what does jointly wide sense stationary process mean? So xt and yt are jointly wide sense stationary processes if one, xt and yt are individually wide sense stationary, and second, expectation of xt into yt plus tau is only a function of tau. So what we will do is we will define. So this is the definition of jointly wide sense stationary process. This is how it is defined. So for showing the ZT is WSS or Whiteson stationary, what we will do is we'll define some notation. So for solving, we'll define mu x as expectation of xt. Since it is Whiteson stationary, anyway your mu x is constant. And we'll define Rx of tau as expectation of xt into x of t plus tau. Conjugate. Similarly, we will define mu y as expectation of yt and ry of tau as expectation of yt into y conjugate of t plus tau. And we'll define the cross covariance of rxy of tau. Since it is only a function of tau, it is given that they are jointly Whiteson stationary, so it is only a function of tau. So this I will define as x of t into y of t plus tau, and we'll have a conjugate here. Now we need to show that zt is w's Whiteson stationary. So what we need to do is we want to show that zt is Whiteson stationary, which means that first thing, show expectation of zt constant, and then show rz of tau, which is expectation of zt into z conjugate t plus tau, is only a function of tau. Okay, so let's start with first one, that is expectation of zt. So what is zt? Zt is simply xt plus yt. So therefore expectation of zt this is equal to expectation of xt plus yt, and this thing is equal to expectation of xt plus expectation of yt. So this is by linearity of expectations. And this we have seen, it is mu x plus mu y. Both of these are constants, which means that this is also equal to, or this is also a constant, which means your mean, what we have concluded is your mean function or your expectation, your mean is not a function of time. Okay, so this first thing we have checked. The second thing we need to check is your autocorrelation function. So let me quickly add a page. So next thing that we need to check is rz of tau. So your rz of tau is expectation of zt into z conjugate of t plus tau. This thing here is equal to expectation of your zt is simply xt plus yt. In similar way, we can write this as x of t plus tau conjugate plus y of t plus tau conjugate. And now we can multiply and get the terms that we want. So first term that we'll get is x of t into x conjugate of t plus tau, plus we will get xt into y conjugate of t plus tau. Then we will get yt into x conjugate of t plus tau and plus we will get yt into y conjugate of t plus tau. Okay, again by linearity of expectation I can separate the terms. So it is expectation of xt into x conjugate of t plus tau plus expectation of xt into y conjugate of t plus tau plus expectation of yt, or I can write this in a different way. So what we are having here is x conjugate of t plus tau into y of t. I'll write it 1 second. Expectation of yt into y conjugate of t plus tau. So I can write this thing as x of t plus tau into y conjugate, one conjugate. Okay, so now here the first term that we are having here is simply your rx of tau. So simply your rx of tau. The second term that we are having here is simply your rxy of tau. So this is how we had defined this. So this is your rxy of tau. The third term here, so the third term here is simply rxy of minus tau. So you have t plus tau here and not with y. So you'll have a minus thing coming here. So what you need to do is you need to take this time index and subtract this time index from it. So t minus of t plus tau will give me minus tau, and you have a conjugate sign here. So what we will get here is rxy of minus tau but with a conjugate sign. Okay, and plus this thing here is simply your ry of tau. So again, if you observe here, all these four terms are only the function of lag. So therefore this thing here is only a function of lag, that is tau. Okay, so if we see, we have looked at the second point also. So what we have observed here is, let me number the equations. This is 1 and this is 2. So what we observe here is first one. So from equation 1, we observe that expectation of z of t is constant, and from equation 2 we observe that rz of tau, which we defined as expectation of zt into z of t plus tau conjugate, this thing is only a function of lag, that is tau. Therefore, Zt is a wide sense stationary process. Okay, so there was a request that I'm going a little bit faster and to go slower. Okay, from next question I'll go slowly, but for this question I'll just repeat the process once again so that it's little bit clear. Okay, so what is said is, let xt and yt, where takes values in real, so these are jointly wide sense stationary processes, and it says that consider another process which is simply addition of these two processes, that is xt plus yt. And what we need to do is we need to show that zt is a wide sense stationary process. So first thing that we looked at was we got an additional term here which is jointly wide sense stationary process. So this particular term here, jointly wide sense stationary, first we need to understand what jointly wide sense stationary processes mean. So what we did, we first defined what is joint wide sense stationary processes. So it says that two random processes xt and yt are jointly wide sense stationary processes if first one, xt and yt are individually wide sense stationary processes, and second, the cross covariance, or sorry, the cross correlation function, that is expectation of xt into yt plus tau, is only a function of tau. So this is the definition of jointly wide sense stationary processes. And if xt and yt are jointly wide sense stationary processes, they should satisfy these two properties. And using these two properties, in order to show this particular thing, what we do is we define some notations just for simplicity. So what we do is we say that mu x is mean of xt, and since xt is wide sense stationary, it is constant with respect to time. So there is no time indexing here. Similarly, mu y is expectation of yt. Again, yt is wide sense stationary process, and therefore this will again not be a function of time. It will be a constant thing with respect to time. Then we defined the autocorrelation functions for the two random processes xt and yt, where rx of tau is expectation of xt into x conjugate t plus tau. Again, it is only the function of lag, that is tau. And then we have ry of tau, which is expectation of yt into y conjugate of t plus tau. So this is again simple definition of autocorrelation. And then we defined its cross correlation, that is rxy of tau is simply expectation of xt into yt plus tau conjugate. So these are simple definitions, some notations that we are defining that we will be using in coming steps. Now what is asked to us is we need to take this zt and show that it is wide sense stationary. Till this point, I hope everything is clear. If you have any queries here, just unmute yourself and ask. So what we want to do in this particular question is we want to show that this zt is a wide sense stationary process. So for that, what we need to show? First thing, we need to show that the expectation of that random process is constant with respect to time. And second thing that we need to show is this autocorrelation function is only a function of lag, that is tau. Okay, so then what we will do is we'll take both of these points one by one. This is the standard approach to show any random process is being wide sense stationary or not. So first thing that we'll see is we'll take up this mean. So we have this zt, or we'll take expectation of zt, where this zt is simply x of t plus yt. Okay, so if you put this zt, sorry, this zt equal to xt plus yt, here we get something like this, that is expectation of x of t plus y of t. Now this expectation is a linear operator. What do we mean by it being a linear operator? This means that expectation of ax plus by, where a and b are constants, is equal to a times expectation of x plus b times expectation of y, where x and y are random variables. So this means linearity property. Now here, for a given time index, xt and yt are random variables, and by using this property we can write it as expectation of x of t plus expectation of yt. And we have defined expectation of xt as mu x, and we have defined expectation of yt as mu y here. So, and we know that since x of t and y of t are weights and stationary processes, this mu x and mu y are constants. And therefore, the addition of two constants will again result into another constant, which is not a function of time. Therefore, this z expectation of zt, the mean, is not a function of time. Therefore, we have checked the first point that we wanted to check. Once we know the expectation of zt is constant, the next thing we need to check is whether this autocorrelation function is only a function of lag or not. So for that, we will consider the definition of autocorrelation function, which is expectation of zt into z conjugate of t plus tau. Now again we have this zt as xt plus yt. So that will substitute here. So we have this xt plus yt, and then we have z conjugate of t plus tau. So that will be xt. So z of t plus tau will be x of t plus tau plus y of t plus tau. But now we have a conjugate also. So we'll have x conjugate of t plus tau plus y conjugate of t plus tau. Now here we have four terms, 1, 2, 3 and 4, and each of them will get multiplied by each every other term. So therefore, by cross multiplying all of these things, we'll get four terms. So this xt will get multiplied by x conjugate of t plus tau. That will result into the first term, that is this one. Then this xt will get multiplied by y conjugate of t plus tau, which will result in this second term, that is xt into y conjugate of t plus tau. Then this yt here will get multiplied by x conjugate of t plus tau, which will result in the third term. And then we have this yt getting multiplied by y conjugate of t plus tau, which will give the third term. Okay, then again using linearity of expectation, we can separate the expectations for all of these terms. So that will give expectation of, so this is the first term, that is expectation of xt plus x conjugate of t plus tau. Then we'll have the second term. Let me change the color. Okay, so this is the second term, just separating them. Then this is the third term, and this is the fourth term. Okay, so for second term, what I did is, so this thing here was some different color. This thing here was basically expectation, or we should use the font also. So here what we actually had was expectation of x conjugate of t plus tau into yt. This is what we had. So I wrote it as expectation of x of t plus tau into y conjugate of t whole conjugate. And then this I can write as expectation of x of t plus tau into y conjugate of t whole conjugate. This is a valid operation. This is the only thing that I did. Now what we had was, we had rxy as expectation of x of t plus tau, sorry, x of t into y of t plus tau, like y conjugate of t plus tau. Now here, so and this is like tau. So this index here tau, we can take it as, let's say this is t2 and this is t1. So this tau is simply t2 minus t1. So t plus tau minus t will give me tau here. So this is simply t plus tau minus t, which is tau. Now same logic we'll have to apply here. So here this is t2 and this entire thing is t1. So when we take t2 minus t1, so for this particular thing, if I take t2 minus t1, this will be equal to t minus t plus tau, which is equal to minus tau. So the inside thing, whatever we are having, is simply rxy of minus tau. And we have a conjugate sign outside, so that will give me rxy conjugate of minus tau. The first term here is simply the autocorrelation function of your x, so that is rx of tau. Then the second term here is the cross correlation function that we had defined like this, so it is simply rxy of tau. Third term we just discussed, and the fourth term that we have here is expectation of y conjugate of t plus tau. Again, this is autocorrelation function of random process y, so this is ry of tau. And since these are jointly Whitesell stationary, your rx of tau, rxy of tau, and ry of tau, and even this rxy minus tau conjugate, all of these are only the function of your lag, that is tau. And since all of these are only a function of your lag, your autocorrelation function of your random process z is also a function of lag only. So therefore, from all of these two steps, what we conclude is, so from equation 1, your mean of your random process z is constant, and from equation 2 we observe that the autocorrelation function is also only a function of your lag, which means that your z is a Whitesell stationary process. Is this question clear now? If yes, I'll move on to the next question, otherwise you can ask your doubts. Okay. Okay, so let me move on to the next question. So here what is given to us is, let yi in the set of natural numbers, so what we have is y1, y2, y3 and so on, be IID Gaussian random variables such that, so what is given to us is, first thing is these are IID Gaussian random variables. What do you mean by IID? So by IID we mean independent and identically distributed, such that expectation of yi and is 0, so these are 0 mean, and variance of yi is given as 4. Now what we need to do is, we need to so what they have done is, they have defined another random process. So x of n, for n in natural numbers, x of n is sum of all of these yi's. So if it is x of n, then you will have first n, or y1 till y1 plus y2 till yn. So if it is x1, it will be simply y1. If it is x of 2, it will be y1 plus y2 and so on. So this is the another random process that they have defined based on these IID Gaussian random variables. What they have asked us to do is, we need to find its mean and autocorrelation function. Okay, so these are the two things that we need to figure out. We need to find its mean and its autocorrelation function. So let's start with mean. So let's start with finding mean. So by that, what we need to do is, we need to find out expectation of x of n. Okay, So this expectation of x of n, this will be equal to expectation of, so now my index here is n. So this will be simply y1 plus y2 plus y3 and so on till yn. Now these are again n random variables, and then we can simply apply linearity of expectation again, and then we will have expectation of y1 plus expectation of y2 and so on till expectation of yn. So this thing here is again by linearity of expectation. Okay, and then it is given to us is all of these yi's are zero mean. So expectation of yi for all i's is 0. So it means that this thing is equal to 0, this is equal to 0, and this is also equal to 0. So for all I from 1 to small n, expectation of yi is equal to 0. So therefore this will give me 0 plus so on till 0, which is equal to 0. So this is the mean. So expectation of x of n comes out to be equal to 0. Is it clear till this point? Okay. If it is clear here, then let me move on to the second part. Next we need to figure out what is sorry, what is the autocorrelation function. Okay, let me add a page here. So next thing we need to find out is autocorrelation function. Okay. Okay. So here what we will find out is expectation of x of n into x of n plus m. I'm not putting a conjugate sign because anyway these yi's are Gaussian random variables, which means that these yi's are anyway real. So even if I put conjugate sign or if I don't put conjugate sign, it is okay. When I have complex random variables, it is mandatory to have a conjugate sign. Okay, so this is what we are having here. So what we will do is we'll substitute what this x of n into x of n plus 1 is. So we can write it as expectation of, so let me start using some colors here. Okay. Okay, so this x n will be simply y1 plus y2 and so on till yn, and this x of n plus m will be y1 plus y2 and so on till y of n plus m. Okay, so what I'll do for concise notations, I'll do this thing. Expectation of summation L equal to 1 to n yl into summation k equal to 1 to n plus m yk. Now this summation here which we are having, I can split it into two summations. So this thing I can write as summation k running from 1 to n yk plus summation k running from n plus 1 to n plus m yk. Is it fine? I'm just splitting it into two summations. So now what we can write it as expectation of summation L equal to 1 to n yl into summation k equal to 1 to n yk plus summation k equal to n plus 1 to n plus m yk. So now what we have here is expectation of summation L equal to 1 to n yl. So here if you observe, these two summations are identical. So this is also 1 to n yk, and this is also 1 to n yl. So this I can simply write as square plus I'll have summation L equal to 1 to n yl multiplied by this thing, that is summation k equal to n plus 1 to n plus m yk. Okay. So now what I have here is I can again apply linearity of expectation and write this as summation expectation of summation L equal to 1 to n yl square plus expectation, the second term, that is summation of L equal to 1 to n yl into summation k equal to n plus 1 into n plus m yk, like this. Now what I can do is the first expectation that I have, or let's take it term by term. Again, I'll use some colors here. So let's take the first term. So we have expectation, and let me number it as 1. Expectation of summation L equal to 1 to n yl square. This I can write as expectation of summation of L1 equal to 1 to n y summation L2 equal to 1 to n yl1 into yl2. Now what I'll do is I'll again split them into two parts. First part will be summation of L1 equal to 1 to n yl1 square plus summation L1 equal to 1 to n into summation L2 equal to 1 to n, where L2 is not equal to L1, into yl1 yl2. Okay. Now again I can apply linearity of expectations, and then I'll have expectation L1 equal to 1 to n expectation of y of L1 square plus summation L1 equal to 1 to n summation L2 equal to 1 to n L2 not equal to L1 expectation of yl1 yl2. Now let us look at this term. This term is basically the second moment, and we can write it as variance of yl1 plus mean of yl1 square, and this comes out to be equal to, so this variance is equal to 4. It is given to us. So this thing is equal to 4 and expectation is equal to 0. Then this term here, since yi and yj are independent when I is not equal to j, I can write it as expectation of y of L1 into expectation of y of L2. And why I am able to do it? Since they are independent. And expectation of YL1 is 0 into expectation of YL2, that is 0, which comes out to be equal to 0. So therefore this entire term now reduces to summation L1 equal to 1 to n, where expectation of YL1 square, that comes out to be equal to 4, which is equal to 4n. So this is the first term in this entire equation. Okay, so this is what we are having here, and now we need to figure out what the second term is. So let me just take up this second term and copy there. Okay, so now this I can write as expectation of summation L equal to 1 to n, summation k equal to n plus 1 to n plus m yl into yk. Again, I can apply linearity of expectations and take the expectation inside the summations. So I'll have L equal to 1 to n, to summation k equal to n plus 1 to n plus m into expectation of yl and yk. Now if you observe here, this L ranges from 1 to n, and this k ranges from n plus 1 to n plus m. This, what I'm trying to say here, that L is not equal to k every time. And in that situation, and we know that independent. So this yk and yl are independent for all L not equal to k. So therefore, this expectation of yl into yk I can productify as expectation of yl into expectation of yk for all L and k, and this thing is equal to 0 into 0, that comes out to be equal to 0. So all of these terms which are inside this summation come out to be equal to 0, and therefore this summation entirely is equal to 0. So this is the second term. So if we substitute this equation 2 and equation 3 in 1, what we get is our autocorrelation function. So therefore what we get is, therefore from, or let me write it properly, substituting equation 2 and equation 3 in equation 1, expectation of xn into x of n plus m comes out to be equal to 4n plus 0, which is equal to 4n. Is it clear? Any questions? So we have found out the mean and autocorrelation both. Okay, if there are no further questions, then I'll move on to the next question. So yeah, there is. This is not autocorrelation. We want to find expectation of. Okay, so the next question is, let xt be a continuous time Whitesand stationary process with zero mean. So what is given to us till this point is x of t is Whiteson stationary process. Expectation of x of t is 0, and autocorrelation Rx of tau is delta tau. And what is given to us is Rx of tau, which is autocorrelation function, which is expectation of x of t into x conjugate of t plus tau. This is equal to delta tau. Now using this random process, define another random process yt, which is integral from t minus 1 to t xu du, and we need to find its mean and cross correlation xt yt. So we are given another random process yt, which is integral t minus 1 to t xu du, and we need to find its mean and cross correlation function. So we need to find out what is its mean and the cross correlation of xt and yt. So let's start with mean. So let's start with the first thing, that is mean of yt. So mean of yt means simply expectation of yt. This is equal to expectation of, what is yt? Your yt is integral, this is your yt. It is integral t minus 1 to t xu du. So this is integral t minus 1 to t xu du. Now we can apply linearity of expectation again. Then we'll have t minus 1 to t expectation of xu into du. Now what is expectation of xu? It is given to us to be equal to 0. So this is a Whiteson stationary process with 0 mean. So this expectation of xu here, this expectation of xu here is equal to 0. So this is equal to integral t minus 1 to t 0 du. This comes out to be equal to 0. So the mean of this random process yt is again equal to 0. So we now have the mean. The next thing that we need to find out is the cross correlation of xt and yt. So let's find out that. So next thing that we need to find out is cross correlation of xt and yt, and that is defined as expectation of xt into y of, or let's say xt1 and yt. Let's not use the lag definition, we'll use xt1 or okay, let's take lag definition only, into yt plus tau conjugate. So this thing is equal to expectation of, what is your xt? Xt is xt, and your yt is integral t plus tau minus 1 to t plus tau yt, sorry, x of u du. Okay. So now what, and there is a conjugate here. So this you can write as expectation of x of t integral t plus tau minus 1 to t plus tau x conjugate of u du. Now what I'll do is I'll do a small replacement. So let this u be equal to v plus tau, which means that your v will be equal to u minus tau, dv equal to du, and your v will vary from v plus tau minus 1 minus tau, that is t minus 1, to t plus tau minus tau, that is t2. So now your v will vary from t minus 1 to t. So by this simple substitution, what we get is expectation of x of t into integral t minus 1 to t x conjugate of v plus tau du, or dv, sorry. And this we can write as expectation of integral t minus 1 to t, this xt is constant, xt into x conjugate of v plus tau dv. Again, by linearity of expectation, I can write it as integral t minus 1 to t x of t, sorry, expectation of x of t into x conjugate of v plus tau dv. Now what we know is, we know expectation of x of t into x conjugate of t plus tau is delta tau, or this is equivalent to expectation of x of t1 x conjugate of t2, this is equal to delta t2 minus t1. So by this second definition, second equivalent definition, we can write this as t minus 1 to t into delta v plus tau minus t dv. Okay, so what it means is, if tau minus t belongs to the range of t minus 1 to t, then this is equal to 1, otherwise will be equal to 0. So this impulse is basically a function of v, sorry, wait, let's do it nicely. Okay, let me copy this integral on a new page. We'll do this properly. Copy, paste here. This is the integral that we are having. Let me draw the axis. So this is v axis, and let me have this region of integration, that is t minus 1 to t. So this is my region of integration that I am taking into consideration, and then I have impulse here. So this impulse I can write as, delta of v minus t minus tau, like this. Okay, so basically this impulse is located at t minus tau. Okay, so now what happens is, if this t minus tau, so this is like this is v and this is t minus tau. This is how your impulse is located. Now if this t minus tau is here, that is, this is the case when t minus tau belongs to t minus 1 to t, which means that your minus tau belongs to, or rather your tau belongs to 0 to 1. In that situation, your impulse will be located inside your area integration region, and in this situation your integral will be 1. Suppose now my tau minus t minus tau is here, somewhere here. That is, your t minus tau is greater than t, which means your minus tau is greater than 0, or your tau is less than 0. Then in that situation, if your impulse is located here, then your integral value, because again your region of integration is still this, so your impulse is not located in your region of integration, your integral value will be equal to 0. And similarly, if you are in this region here, so if you are having your t minus tau somewhere like this, so if your t minus tau is here, that is your t minus tau is less than t minus 1, or your tau is greater than 1 here, again your integral value will be equal to 0, because again your region of integration is somewhere here and your impulse is located here. You're outside your region of integration. So whenever your t minus tau, so what we are concluding is, when your t minus tau belongs to the integration region, which is equivalent to writing your tau belonging to 0 to 1, then integral t minus tau to t minus 1 to t delta v minus t minus tau dv comes out to be equal to 1, and this is equal to 0 otherwise. Okay, so therefore this expectation thing that we are having, let me write it. Therefore the cross correlation function that is expectation of x of tau, x of t into y conjugate of t plus tau is equal to 1 if tau belongs to 0 to 1, it is 0 otherwise. Is it clear? Any questions here? Okay, if there are no questions, then I'll quickly move on to the last question for today. So this is an important question when we will be considering communication systems where our noise will be additive white Gaussian noise. So what it says, what this question says is, let x of t be an additive white Gaussian noise process. So what we mean here is x of t is AWGN. So for that, your expectation of x of t is equal to 0. And let's say the autocorrelation function Rx of tau is n0 by 2 delta tau. Let me define it in this way. Now another thing that we are defining is xi is integral minus infinity to infinity xt into phi I of t dt. So you have, this is a random variable here. So this xi is simply integral minus infinity to infinity x of t into phi I of t dt. So how we can interpret this is, you're projecting x of t on phi I of t, where this phi I of t for I equal to 1, so I equal to 1, 2, 3 and so on till n. So this particular notation, that is square bracket n, is in general a set from 1, 2, 3 and so on till n, where n belongs to the set of natural numbers. It's a set of orthonormal function. So this phi i's are orthonormal, that is integral minus infinity to infinity phi I of t phi j of t dt is equal to 1 if I equal to j, it is 0 I not equal to j. So this is what we mean by orthonormal functions. So what this particular xi is, it is orthonormal projection of AWGN. Okay, and again this xt is a random process. So since xt is a random process, your xi will be random variables. Another thing to note here is this x of t is Gaussian process. Since x of t is Gaussian process, your xi, since x of t is like a linear combination of Gaussian random variables for different t's, xi we can interpret as linear combinations of Gaussian random variables, and hence these are Gaussian. So this xi is a Gaussian random variable for all I in the given set. Okay, so xi is a random variable, xi is a Gaussian random variable when we are having this particular form of projection. What is asked is we need to comment on the distribution of the random variables xi to xi for I in the given set. So one thing that we know is it is a Gaussian random variable, and now if we want to comment on its distribution, since it is Gaussian random variable, it is sufficient to know their mean and variance, or let me say covariance, to describe or characterize the random variables xi for I in n completely. So for Gaussian random variables, it's sufficient to just know the mean and covariance matrix. Okay, so let's first look at its mean. So what do we mean by mean? So we'll look at expectation of xi, which is equal to expectation of, it is ith projection, so minus infinity to infinity, you have your Gaussian process xt into phi I of t dt. Now by linearity of expectation, I can take expectation inside, so it is integral minus infinity to infinity expectation of x of t. Now the only random thing in this integrand is xt, so we can write it like this, into phi I of t dt. Since xt is additive wide Gaussian process, we know that expectation of xt is equal to 0. So this thing here is equal to integral minus infinity to infinity 0 into phi I of t dt, which is equal to 0. So what we conclude is expectation of xi is equal to 0 for all I in this set n. So this we know. Now let us look at the covariance. So we will look at covariance of xi xj, which is simply equal to expectation of xi minus its mean into xj minus its mean, which is simply equal to expectation of xi into xj. So therefore this we can write as expectation of integral minus infinity to infinity integral minus infinity to infinity x of t1 phi I of t1 dt1 into integral minus infinity to infinity x of t2 phi I of t2 dt2 sorry, not phi I, phi j. Then we will have expectation. This we can simplify as two integrals outside x of t1 x of t2 phi I of t1 phi I of t2 dt2 to dt1. Okay. Now again I can apply linearity of expectation. So that will give me integral from minus infinity to infinity, integral from minus infinity to infinity. Again, the only randomness is in this xt1, xt2 and not here. So this we can write as expectation of x of t1 into x of t2. Outside we can write as phi I of t1 into phi I of t2 dt2 into dt1. Now this thing here is simply your autocorrelation function. This you can write as t1 plus tau. So therefore this is simply your t1 plus, this is your r of tau, where your rx of tau will be equal to t2 minus t1, and your rx of tau we have defined as n naught by 2 into delta tau. So this thing here will be equal to n naught by 2 into delta t2 minus t1. So let us substitute that. So what we will get is integral minus infinity to infinity, integral minus infinity. So now again, this inner integral is with respect to t2. This as j. So this thing here is only a function of t2. This is a constant. We can take it outside. So we can write this as phi I of t1 into integral minus infinity to infinity n naught by 2 delta t2 minus t1 phi j of t2 dt2 into dt1. Now if you just consider this particular part, or okay, what we can do is this n naught by 2 is constant, we can take it outside. And another thing that we can do here is, by shifting property, this is equal to delta t2 minus t1 into phi j of t1. And again, this is constant and this phi j of t1 is constant, and I can take it outside. So equivalently, now I can write this as equal to integral from minus infinity to infinity n naught by 2 phi I of t1 into phi j of t1 into integral minus infinity to infinity delta t2 minus t1 dt2 into dt1. And this is simply integration of an impulse, so this thing is equal to 1. So now what we are left with is n naught by 2 integral minus infinity to infinity phi I of t1 into phi j of t1 dt1. And we have seen this integral earlier. We have seen, since it is an orthogonal or rather orthonormal functions, so this phi I of t into phi j of t integral is equal to 1 when I equal to j, and otherwise it is equal to 0. So this particular integral here is equal to 1 if I equal to j is equal to 0 if I not equal to j. So therefore this comes out to be equal to n naught by 2 when I equal to j is equal to 0 when I is not equal to j. So this is what we have obtained now. So what we are having here is expectation of xi is 0. Your covariance of xi comma xj is n naught by 2 if I equal to j, and 0 if I not equal to j. So basically it says that your variance of xi, that is your covariance of xi comma xi, this thing is equal to n naught by 2. And since covariance of xi and xi and xj are for I not equal to j are uncorrelated, which means for Gaussian they are independent. So what we have now is this xi's are Gaussian distributed with 0 mean and n naught by 2 as variance for all I in this range, which means that these xi's are IID Gaussian random variables with mean 0 and variance n naught by 2. So this orthogonal projection will come up when we are having different modulation schemes, when we project it on basis and all those things. So this is an important concept, that orthogonal projection of AWGN will lead to IID Gaussian random variables with 0 mean and variance of n naught by 2. And this is useful for communication systems and an important thing to look at. So that's why I covered it in this particular lecture, because we looked at AWGN in this week. If you have any questions in any of the content that I covered today, please feel free to ask. This is all that I had to cover today. If you have any questions, then please ask. Otherwise, you are free to leave the meeting. Thank you for attending today's session.